So I will talk a little bit today about excitons and some works that we have done to understand pump probe experiments. So it's features of the Jumbo code that has been used in the last year, but has not been released, let's say, for the public version of the code. So today I would like to explain this more in detail, and I will focus on 2D materials because it's let's say the topic that I have been working in the last years. So basically 2D material, you have a bunch of them nowadays, no? You can find metals or semiconductor, insulators, magnetic materials. In this talk, I will present work that is focused on transition metal decalcogenides that are semiconductor with a gap around 1.8 electron volts. And I will introduce some calculation of a novel family of semiconductor and magnetic semiconductor that are the transition metal trihalides. That they have a particularity, and is that the lattice, so the stoichiometry is, for example, bismuth iodine 3, because you have a missing atom in the lattice. So the new thing of this material is that because you have this kind of hole, the dielectric screening is reduced a lot in comparison with let's say a normal 2D semiconductor that has already a very small screening, no? Why this is important in the optical properties is, okay, I mean, we have already 2 days here and people has introduced the concept of dielectric screening already. So, but to talk in practical terms, when you have let's say, a normal bulk material, infinite in the three direction, usually the binding energy, the dielectric screening is, let's say, normal, you can think in an isotropic tensor, and the binding energy of an exciton that you can calculate with the Bethe-Salpeter, as we will see in the next talks and in the hands-on today, has values typically of 20, 40 millielectron volts, like in the case of gallium arsenide or silicon or any, let's say, bulk semiconductor. When you go to 2D materials like MOS2, you reduce the screening a lot because basically you take a material out. It has particularities, as we saw yesterday in the talks of the GW. And the exciton binding energy can grow a lot, no? In TMDs, you are in the range of 100, 200 millielectron volts, not electron volts, okay? First typo of the day. So, and then in other semiconductors, you can go up to 2 eV, really 2 eV. Like, for example, boron nitride or this family of the three halides, no? And so this is very important because then you can observe excitons at room temperature, and you can discover many properties of the material that before, when you were in the case of the bulk, were not detected or only detected at very low temperature. So this was limiting the number of, let's say, groups that could study the physics of exciton. So also the 2D material like the MOS2 and the family of transition metal decalcogenides, they have a changing character of the gap with the number of layers. This is more or less it's happening in all the 2D material, because basically when you start to stack different layers, you change the band structure. And it can happen that you go from a bulk that is indirect semiconductor to a monolayer that is direct semiconductor. And here is a little summary of the, let's say, the exciton properties of MOS2 single layer, where this is the gap that you calculate with the GW, and this is the binding energy that you calculate. So this is the exciton peak that you calculate with Bethe-Salpeter, and this energy difference is the binding energy, no? So this exciton X, the A and the B exciton, so-called in MOS2 and other TMDs, They come from the gap that you have at the point K. And as you see, they are very localized at the K space in the Brillouin. And okay, they let's say they spread over several unit cells when you plot the exciton wave function. So this we will see later in detail in the hands-on of the afternoon. And when you go to other semiconductors, like the case of bismuth iodine 3, but if you go to magnetic semiconductor like chromium iodine 3, the physics of the exciton is very, very similar. Now imagine, or you can imagine that here I have taken out one atom of bismuth or chromium. So you reduce the screen really a lot, and then you are starting to be like in a molecular material, no? And then already in the bulk that is here plot, you have a very large binding energy that is around 0.24 eV. That this is a bulk, infinite material, but it has the binding energy that you can find in a single layer of MOS2. So this is important because then basically you don't need to exfoliate down to a single layer. That is very difficult in most of the materials. With this material, you exfoliate the bulk. I mean, but let's say without taking care of how many layers, and already you are in the range of a strong excitonic effect. Of course, if you go to the monolayer, the binding energy increases until 0.8. But I already tell you that to obtain monolayer of bismuth, iodine 3 is not easy. No, usually up to 3 is let's say, the limit that they have seen so far. But okay, who knows? Maybe with a molecular bin epitaxy, they can achieve a monolayer. It's not our work to grow the sample. No, enough we have with the simulation. So, and what about the pump and probe? Once you have let's say that once you have done your calculation of the excitonic properties at the ground state, you have let's say 2 main paths, or you study them with a photoluminescence or absorption that, let's say, are time-independent spectroscopy, or you go to time-dependent spectroscopies. How they work? Basically, you go with a pump that excites the sample, it's a pulse, and then you go with a probe that is also a pulse with certain delay with respect to your pump. So basically, you are probing the optical properties of the system that is already excited. No? So basically, what is in this plot. So there are many experiments that you can do. No? I will present here just a few of them, and then some of our calculation that we did in the last year. So, for example, you can measure transient absorption or transient reflectance. Basically, what you measure is a spectra that will change with time, and most of the time is presented like in this axis you have the delay of the probe with the pulse, and here you have the full spectra. Usually, okay, this is presented in that way. We will go in detail to this figure later. So here is another work that this was done by Margherita, Davide, Andrea, I think the experimental group of Stefano Alconte and Giulio Cerullo. And here you can see a little bit better. This is the absorption, the ground state absorption. So you go with a pump pulse at these 3 values, A, B, and C. And then with the probe, you are measuring absorption as a function of time. What you plot here, this is the differential absorption. So it's the absorption that you measure with the probe minus, let's say, the reference without excitation. So typically you see areas where you have, let's say, minus, that are the blue areas, and areas that in red that is larger or positive differential absorption, no? And are the 3 cuts of the measure at the energies that are marked here, at the exciton A, B, and C. So basically, in some energies, you have a, let's say, abletion of the absorption. This you can see like you have generated electron-hole pairs. So they are already occupying available states. So you decrease the absorption of your material. Of course, the effect is small. You can see at the percentage. It's 0.4%. It's a small effect, but that you can measure and very well, as is here. And then you can see that you have different times, let's say, for the differential absorption to come back to, let's say, the normal or the ground state. No, you can see that when it goes to the green, it's going to 0. So it means that you recover the. Here is one pump, but it's you have. I guess you can tune the energy. Yeah, it's different pump. Yeah, here is different pumps. Yeah. A, B are resonant with the excitation. You have 3 different pumps, and for each pump, you do this plot, let's say. This is the probe, this probe energy, no? And another kind of experiment that you can do, or I mean, the setup is very similar, and this was also, I guess, that introduced yesterday by Enrico, is where you go with a pump, and then you are measuring differential absorption or differential reflectance, and you observe that your signal is vibrating. No? If basically, if you plot the, let's say you choose an energy and you plot this, the value of the differential reflectance or absorbance, depends on your setup, you see that it's oscillating, and of course, these oscillations are not random oscillation. When you do a Fourier transfer of this oscillation, you discover that they correspond to a phonon. No? This you can check by, for example, doing the Raman spectra of this material. You will see a series of peaks, and one of those frequencies will match with the frequency of a coherent phonon. Indeed, this experiment can be more general. You can excite a coherent magnon, you can excite a coherent phonon, whatever that it can couple, let's say, exciton with another quasi-particle or another excitation. So this also can be done experimentally. And okay, so let's say that so far in the Jumbo code, we can calculate by an approach of finite difference which phonon modes couple more strongly to light. No? But this simulation of this is a little bit more tricky because involve together exciton and phonons. So this is more or less a similar experiment. This is a pump-and-probe reflectance, where it's similar to the previous that they have explained, but here is applied for bismuth iodine 3. And here we have a little bit more of detail, more detailed experiment. So you can see that this is the signal that you see. It's oscillating. When you subtract the background, you can analyze better this oscillation. And when you do the FFT, the Fourier transfer that is in red here, you see that it matches with one of the Raman peaks. This is something to study more in detail. Why is coupling only to one phonon peak and not to the, let's say, complete set of peaks that you see in the Raman? That is also an exciton phonon consequence, let's say. And okay, and here, okay, see more or less for this experiment, one calculation that is possible is you can calculate Bethe salpeter, displacing the atoms according to a phonon mode. This will give you a kind of decoupling of the exciton phonon. Okay, so and last, let's say, last option to study exciton in the time resolve in a time resolve experiment will be, and this is, let's say, for me is more recent, are the time resolve ARPES experiments. So we had yesterday a talk of Federico, very good about the ARPES experiment, where you can basically measure the electronic structure. No, you obtain a map of the band structure with all the details and particularities of the experiment, but let's say that the output of ARPES is this band structure. But what you can do is to excite the sample optically with a pump. And then your probe will be a ultraviolet normal ARPES probe that is with energy that is more than 20 eV. So you will have also the band structure, but of course you can see that you have some dots that are the excitation that you are inducing by this pump, no? And okay, so let's say that people are thinking that those are the excitonic signature in the ARPES. You can see this also like when you dope a material, if it has a small band gap, you will see that you are filling conduction band in the ARPES experiment. Now, this is kind of optically doping a material if you want to see like that. Okay, I will say that this is a very recent topic that will, for sure, will have a lot of development in the incoming years, and of course, it's I think Davide will also talk of this more in detail later. So, so far, until day 3 of the school, we are in this position. After you follow the tutorial of the GW that was yesterday, and you do the tutorial of the salpeter, you are in this position. Basically, you can calculate your bands, you can calculate the correction of the bands, and you can calculate your exciton with the salpeter. And so far, we are in the ground state situation. So after that, okay, we have learned many things. The GW calculation, the exciton with the salpeters, we know how to compile Jumbo, etc. But what we want to do is to study what's happening if you can with light, and then you excite carriers to the conduction and to the, so you create a population of electron holes in the valence and conduction bands. Of course, they will scatter, for example, with phonons, so you will have to consider the electron-phonon scattering, and also they can recombine radiatively or not, no? So this can be also calculated, and this is what you need to calculate the pump and probe experiments. So basically, it's similar to have a Boltzmann equation at the end, no? It's much more complicated, as we have seen. So the formulation of with the Kadanoff-Bain theory and non-equilibrium green function theory is much more complicated than that. But what you want at the end is, okay, I put my carriers in a set of bands, and I want to calculate how the occupation of these bands change with time. Of course, if you want to populate in the right place the carriers, it's not as simple as a Boltzmann equation. You need to put the pump, so the excitation of the laser, to populate the bands that you are indeed populating with the experiment, no? So, and for this is very useful, the implementation that we have in Jumbo, that basically this part is the equilibrium part, and then you have this is so the formulation that is done with the non-equilibrium green function theory. And basically, what we have here is that this is the part that you obtain with DFT plus GW plus beta salpeter. No, plus, sorry, up to GW. Then you can put the electron hole correlation that will depend on time. And here you can put the interaction with the pump pulse. And this is, let's say, general. So you can put any kind of pump pulse. And this will be very useful for the experiment that we are going to present. So here, this density matrix, you have in the diagonal, you have the occupation of the energy levels. So this will be the diagonal part. And in the off-diagonal part, you can define the polarization, no? So basically, and you will see later on in the tutorials, you can calculate the polarization as a function of time. If you make the Fourier transform of this, you get the Bethe-Salpeter calculated, let's say, in the time domain. If you put on top of the Bethe-Salpeter that you calculate with the normal Bethe-Salpeter, must be on top. And here is not on top because, okay, convergence of different calculation is always very tricky and so on. But basically, if you want to, let's say, you want to know that your calculation is well done before calculate transient absorption, you can check if the Bethe-Salpeter in the time domain fits much with the Bethe-Salpeter in the normal domain. And so with this, we have the coherent evolution, and we can, for example, check what's happened when we put a circularly polarized pulse. No? In the case of MOS2, I will explain this later on, the value K and K prime are different in the response to light. So when you excite with a circular pulse, you populate only one valley. So if you are not introducing any scattering, your pump will basically populate that valley, and the carriers will stay in the, let's say, this initial occupation. No? So, and what are the effects of doing that? So, basically, what are the effects if now we calculate the, let's say, the properties, the optical properties of the material with the carriers in the bands, no? Imagine that, okay, I have a population of holes and electrons, and I want to check GW, and I want to check Bethe-Salpeter, no? And then I can calculate the absorption. The difference between this absorption and the previous absorption will be the transient absorption. So you have one important thing is that the population will change the dielectric screening. So this will have an important change in the GW and in the Bethe-Salpeter. So it's not, you cannot calculate directly Bethe-Salpeter on top of this partial occupation with the GW of equilibrium, no? Because if not, it won't fit the experiment. Here we can see better. If I calculate the Bethe-Salpeter, and then I calculate the Bethe-Salpeter with the occupation in the kernel, I have a strong blue shift. But I have a strong correction of the quasi-particle energies in the opposite direction. So the global effect is this, the purple or the pink line. You can see that if you only consider one thing, you will be totally, let's say, off of the real effect. And this is what is called Pauli blocking. Here in this work of Margherita and Davide, they explain very well. So if you just consider occupation, you don't take account band gap renormalization, then you see that your spectra, you capture the bleaching, but nothing else. When you put the band gap renormalization, of course, you are introducing more changes in the electronic structure and in the Bethe-Salpeter. And of course, these spectra look much more like the experimental one. No? Okay, so it was the coherent part, but of course, this is only one part of let's say the reality. Here you have also the scattering mechanism. This can be any scattering. So I will talk only of the electron-phonon because this is already enough complicated. Here, let's say that this scattering mechanism change they are like a time-dependent lifetime and so on. But you can see them like if in your bands you have a finite width, no? In this figure, you have the dotted lines is the electronic structure, and the let's say this the orange is the real width of your particle. So basically, because your particles or electron hole they have a finite lifetime, they can scatter to let's say to other states. No? And this is what we call the collision part in the dynamics. For example, now if I put a circularly polarized Gaussian pulse here in a TMD, you will populate one valley, but now when you put the electron-phonon, carriers will scatter. They will scatter inter-valley and intra-valley. because they can scatter to other states that are here and to other states on the another valley. This you can measure as well. How? You go with a pump in one valley, that this will be the pump at the A exciton, and you can probe with the same circular polarization with another energy. Then what you will see is, this is the collection of transient absorption data. What you will see is that depending on the probe, if it's at the A or B exciton, you will have a different time behavior of the transient absorption. No? And you can measure, let's say, the time that you need to reach the maxima here, this is the rise time, and you will see that it depends on temperature. Okay, so let's say that this time decreases with temperature. So this is something that you can calculate with Jumbo. Basically, you do the calculation with the pump, and you can calculate the occupation in the 4 valleys. So in this state, here, 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 and here, in all of them. So here is the red is the population at this valley, and the blue is the population here in these 2 valleys. Indeed, I don't show the calculation, the population and the valence band. Only conduction band is what is measured there. So, and this is rather similar to what they measure. But, so we also could compare what's happened with our occupation when we increase temperature, because you can include temperature in this simulation, and you observe that indeed the rise time, so you populate faster the valley, the blue valley, let's say, if you are increasing temperature. So this is another thing that you can calculate. And of course, because we have a general pulse in the equation, we can change the polarization to have the inverse circular polarization, and then probing with A or B energy in the another valley, we will see this is the pink and the clear blue dots. You will see the optical response on those valleys, and this we can also calculate. So this is an example of intra-valley and inter-valley dynamics that you can calculate so far at the level of you are pumping the exciton, and then you are propagating with the electron-phonon dynamics. And okay, here I will be brief in this, because this is basically what I have told you about the change in the screening. You can, of course, do a more detailed experiment. This was done by Valerie Smechal and also Andrea and me in collaboration with the group of Julio. So here, what you realize is that in the experiment you have different times depending on the pump of the laser. And why this is happening? So basically you have a delay. So let's say the time-dependent response change with the pump energy, and you can assign this that you are populating different region of the Brillouin zone. So this we see that in the experiment, in the simulation, for when you change the pump frequency, you are changing the let's say the areas of the Brillouin zone that you are populating, no? And this, of course, change the dielectric screening and change the optical response. No, here you can see how the screening depends on time, and how different is of the pump energy. So this it was used to calculate the population at the let's say the areas where is the A and B exciton, and to compare with the experiment and how this, and then what you have to check is where the maxima is reached, and if this comparison for different excitation follows more or less the experimental trend. And okay, so with this you can also get a nice overview. So, and the last thing that I would like to introduce is, let's say, another kind of experiment that is maybe familiar for you, that is time-resolved Kerr effect. Here, in normal Kerr angle spectroscopy, you can have a magnetic material. Imagine that is semiconductor. You go with light that is polarized in plane. or linearly polarized, and it will have a rotation of the polarization angle depending on the magnetization and on the spin-orbit coupling. You need to have a strong spin-orbit coupling or enough strong spin-orbit coupling to have a Kerr effect. No? So this you can measure time independent, of course. But we will see that we can measure also time dependent this thing. So this technique is usually employed in magnetic material. For example, you have a ferromagnetic material like chromium iodine 3 that it has a out of plane magnetization, and chromium iodine 3 has a strong spin orbit. No, so you can check that. You can take, for example, the full family of chromium 3 halides, that they are chromium iodine 3, chromium bromine 3, chromium chlorine 3. And you see that the ligand has, iodine has a high spin orbit coupling, but chlorine has a very small. And chromium has also a very small spin orbit coupling. No? So in principle, you should see that the Kerr effect of this material will decrease. And the Kerr effect is something that you can also calculate with Jumbo. Why? Because you can calculate the off-diagonal part of the electric function, and this is related to the Kerr angle. So if you do Bethe-Salpeter, normal Bethe-Salpeter calculation, these materials are semiconductor, but a little bit special because they have a chromium atom, so they are not a standard semiconductor. They have a Bethe-Salpeter that is a little bit difficult to understand. But if you calculate the Kerr angle, the dichroins, that it will be the absorption for right polarized light minus left polarized light, you will get what is a change. So this will be the yellow is a plus and the green is a minus. So you will have a dichroins because these two responses are different. In a TMD, they will be identical. So you will have a dichroins that is 0. And when you calculate the Kerr effect, indeed, what we saw is that chromium iodine 3 has the larger response, and chromium chlorine 3 has a very small response. So with this, we know that with Jumbo, we can calculate Kerr effect. No? Why I tell you this if it's not time resolved? Because you can induce a Kerr effect in a non-magnetic material. How? For example, in the TMDs, you can go with a circularly pumped pulse, what I saw before, what I have explained before, and you will populate just one valley. This one valley will generate like a pseudomagnetic polarization in the material. And when you go with a linear pulse, you will observe a tilt of this polarization. So it's like for a few picoseconds, your material become magnetic. No? And this you can measure with a time resolved Kerr setup. And okay, so can we demonstrate that this is what is happening with Jumbo? We can indeed, because we know how to excite a material with circular light. We did before. We can introduce scattering mechanism, that electron-phonon, and we can calculate the Kerr angle at any time. So indeed, this is what we did. The experiment is you go with a pump pulse propulating carriers here, and then with the probe, you will see that the Kerr angle depends on time, no? So basically, this is what you see in some of the experiments. This is Kerr rotation, and you can see that the Kerr rotation decreases faster when you increase temperature. And okay, this is the experimental and some theory based in models. So basically, what we did is you go with a pump, you populate here, circular pump, and then we leave the system to relax, and we can see that at the beginning, valence and conduction band, they are populated only in 3 corners of the hexagonal Johnson, and then with the time, you get an homogeneous population. No? But to get the homogeneous population, of course, you need to put the right scattering mechanism. So that is what we do. And to compare directly with the experiment, what you have to do, you need to calculate the Kerr angle for any time or for a set of time. No, that is what is here. Here we calculated that the independent particle approximation, the Kerr angle, and okay, you see that the signal is decreasing with time, and you can also see that you have indeed several type of dynamics in the material. For example, electrons, they scatter from intervally much faster than holes that they scatter much slower. And this is related to the, because this is basically a spin up 99% and this is a spin down 99%. So the electron-phonon matrix element from here to here are very small. And here they have just more paths to scatter. Now, so here is, okay, we did the comparison with the experiment and it was more or less fine. And also what we estimate as the time, as the lifetime of the Kerr. Okay, so with this, I would like just to finish with the time resolve ARPES. This feature is not so far implemented, but okay, we are working a little bit on this kind of physics here. In the experiment, you are populating, let's say, excitonic states or conduction band states. I don't know very well what you are populating there when you do time resolve ARPES. But so far with Jumbo, you can calculate your electronic bands and you can calculate your excitonic wave function on the bands. No, this you can do with Jumbo and with Jumbo Pi. And this is so far your excitonic wave function. So one option is what Davide proposed in a recent paper that he published in Physical Review Materials last year or 2 years ago, where you can a first estimation for this ARPES intensity if you put exciton population is basically that you will get a copy of the valence band structure with the excitonic intensities. No, if in this case I just saw a simplified approximation, I get one exciton, the first exciton of bismuth iodine 3, and then I calculate what will be the intensity of the ARPES signal for one exciton. Of course, the reality is more complicated because you will excite exciton, they will propagate, and then you will have here, let's say, a not more complex spots. It will be maybe a simple spots, but with a lot of contribution. No, it won't have this clear profile that I'm showing here. But the important thing of this is that material like bismuth iodine 3 are very useful for this kind of experiment because what you need is a very high binding energy. I mean, a very large separation between the conduction band and the exciton in order to observe, let's say, net excitonic effects that you don't get, I don't know, mixed with the conduction band. Okay, so for that I will finish the talk. I would like to advertise our doctoral network. So here in collaboration with Davide Sangali and other colleagues from like Sivan from the Weizmann, Mirta that is also in the audience, and Enrico that was yesterday, a doctoral network that is basic in time resolve simulation of ultrafast quantum materials. So we are, it will be launched in 2024, and okay, we are looking for candidates to make the thesis here. It's a network that will be more or less based at so it will be time dependent oriented. And so far, we have, I guess, a very nice collection of different European countries. And more or less, almost all of them are also winner of the Eurovision contest, except Germany. So this is breaking my statistic. And okay, for this, I would like to thank you for your attention and also our sponsor. And I wait for your question. Thank you.
So, open for questions.
Hi. Thanks for the very nice talk. I'm Pushpendra. I'm from IIT Kanpur, India. So my question was, there was a band gap renormalization and excitonic peak renormalization in one of those results. So how to explicitly measure normalization in the band and then renormalization into the excitonic peaks? Yeah, how do you extract the data for the band gap renormalization and then the effective?
So I'm not sure if I understood the question. So basically, you have to calculate the renormalization at the GW level, at the salpeter level. But what you see in the experiment is the combination of the two.
Okay, but from our simulation point of view, how do we see the total effect in the renormalization, the band opening, increasing and decreasing in the band gap, and then their effective consequence on the binding energy?
The consequence on the binding energy. Yeah. Okay, I don't remember now, but I guess if you increase the band gap, the binding energy will be larger, I guess, and the GW renormalization will be smaller. No, but the thing is that this you have a partial cancellation, so the global effect, you don't know a priori if it will be increasing or decreasing the band gap.
Can I ask one more? Okay. So in one of the dichroism results, was that magnetic circular dichroism or chiral dichroism?
In which one?
CRI3.
In the CRI3,
yeah,
is magnetic.
Okay, thanks. Okay. So now Yambo can do that, right?
Yep. Okay, thanks for the nice talk. I am Line from the University of Southern Denmark. So I'm quite impressed with the amount of different effects you can include. Can you comment a bit on which kind of computational resources you need to do this, where you have both the renormalization and the electron-phonon scattering included?
Okay, yeah. In terms of computing time, I will see that what is the time evolution is like let's say a normal Bethe-Salpeter calculation. But of course, when you calculate, let's say, well, electron-phonon matrix element also, they require a bit of time. But okay, I don't remember very well the estimation of time. But let's say that it's like 2 days work of a full-time simulation. But they are not much more difficult than a normal BSc. It's more a question of dealing with the database of the occupation to, for example, calculate the transit absorption and so on. This is what is more demanding.
I have a question. So from the very beautiful results you showed, it seems that you are able more or less to solve the equation of the universe. No. So I mean, it's a very complicated process, and can you just to point out which are the main approximation and limitation, what you cannot achieve or what you are not achieving in a very clean way?
You know that there is always a trick, no? So, for example, it's I like this one. There is something that they didn't comment, but I will comment. So when we excite with light, we are exciting, let's say, an exciton, no? So we go with our pump, and Andrea will kill me, but let me finish, you know. But you had the micro yesterday. Now it's over. So basically, imagine that you excite an exciton with the light, but when we propagate these guys here, so let's say that we do the following trick. we put our exciton excitation in the energy level of the electron and the holes, no? And then electron and holes, they disperse as electron and holes, not as a bound exciton, for example. This is one of the, let's say, critical approximation. Why is down? Because still we don't know how to propagate an exciton-phonon, or at least how to propagate as efficient as you propagate an electron and hole. It's justified somehow, yes, because the energy changes that you have when you scatter from an electron state with a phonon to another electron state is smaller than the total energy, that the, let's say, the bound energy of an electron and a hole. So you can see, for example, this approximation as a small renormalization of the, let's say, of the exciton state. Of course, the complete thing is to propagate everything at the same level of approximation, but so far it's not possible. This is one of them. There are more.
Thank you. It's important to know that there are limitations. Other questions? Mila.
Thank you. For the ARPES, how do you get these graphs? Do you process current separately for different K points and then do the Fourier transform separately? How do you? Yes, in the ARPES, because you need the K path and you need specific K points. The pump probe ARPES? Yeah.
ARPES is the technique is clear. You excite with a pump, and you do ARPES on top of an excited material. This is not. There is no. There is. I don't think it's there is.
You sum the total current that you Fourier transform and somehow or you select specific K contributions.
I think you select a specific K point, a specific path.
There are other questions? Yes.
Thanks for this talk. Actually, now we are working on exciton formation probed by time-resolved photo emission. And we have a problem that we want to include the inter and intra-valley scattering between K+ and K-.
Okay.
To the population, since I mean, K+, it's not 100% how to say, the polarization, it's not 100%. If we excite by sigma plus or sigma minus, there are always this scattering. So it's, in Yambo, there is a way to include this scattering.
The scattering between K
Between,
plus and K-.
yes, the inter and the intra-valley scattering.
Well, in principle, with the, I mean, the scattering, for including the scattering, you need to include the scattering mechanism. With electron-phonon, you have one of the scattering mechanisms. I don't know if you mean to at the level of the coherent evolution, or
yes, exactly.
This I don't know. I don't remember now.
So actually, we are blocked in this step.
Maybe David has a comment on that. Yeah.
Just a very general remark. I don't want to enter too much in the details. So since this is a school, and then the goal of the school is to keep, let's say, to teach what are the more basic parts and also what is the standard. But then we wanted to have a talk which again was showing what is done as the forefront of research. So first of all, a disclaimer. Alejandro has shown simulations with Yambo, but many of the simulations were done with a private version of the code, so it's not fully released. So you will not be able to do all the dissipation mechanisms that you are looking into. And then in particular, this topic of the exciton dynamics, I think you're referring to this electron exchange mechanism. Yeah, it's okay. It's not trivial to do that. Yeah.
That's also an important point that I am not sure that all the methodology that has been shown is a well-established methodology. I mean, it's really the forefront, and it is debated. I mean, not all the community is has the consensus that is the right way to calculate these quantities, and this is important to know. No, okay, but okay. You can then discuss with the real-time guys. There will be a session. Okay, so I think we need to move on.